In this video, we're just going to do a couple practice problems with U-Substitution just to refresh your memory on what U-Substitution is, how it works back in Calculus 1 so that you're ready for Calculus 2. These are the 4 practice problems we're going to do. I recommend you pause the video, try to work them yourself before you watch me work them. All right, so let's go ahead. Let's look at the first example. So with U-Substitution, we're reversing the chain rule. So I'm always looking for that inside and outside function. So here, this x squared plus 8 looks like it's been plugged into another function. So that's a good thought to try for you. Now, his derivative, du, is going to be 2x dx, because derivative of x squared is 2x, derivative of 8 is 0. If I picked the right u, I should be able to find du's equivalent in the problem. I have the x I need, I have the dx I need. I'm missing the 2, but constants aren't a problem because we can multiply by 1 in a clever form. So I'm going to multiply by 2 over 2. Now I have the 3 pieces needed to make du because they are the equivalent of du when you put them together. That lower 2, that 2 from the denominator that balanced out the 2 I needed, he's just going to hang out with the integral. Technically, it's our constant multiple rule. So I have a 1/2 out front because that's the original 2 in the denominator that I did not use. Now, rewriting my integral. The x was used in du, so I don't need to write him in. X squared plus 8, that's my u, and it's to the 1/3 power. The dx is part of du. And the 2's are taken care of because one of them was in du, one of them was outside. If I plug u and du back in to my new integral, I should get back to the original integral. All right, now this is just the reverse power rule. So we add 1 to the exponent, divide by that new exponent, put our plus c. Okay, divide by a fraction, we need to multiply by the reciprocal. So we get 3/8 u to the 4/3 plus c. I started with x's, so I have to end with x's. So u can be replaced with his equivalent, x squared plus 8. So I get 3/8 times the quantity x squared plus 8 to the 4/3 plus c. That's my final answer. All right, let's go on to the second problem. So here we have trig functions and we have endpoints. So same idea, but a little different. When you deal with sine and cosine, it can sometimes be hard to figure out your u, because you say, well, sine's derivative is cosine, cosine's derivative is sine, so they both seem reasonable. So let's see what happens if you pick the wrong one. So if u is sine x, then my du would be cosine x dx. The problem is this du has a cosine x in the numerator times a dx. This cosine x is not in the denominator. So if I tried to do the same thing I did with the constant with the 2 in the previous problem, to create my du, I actually made this integral worse. Now I have a cosine cubed in the denominator. So that is not a good idea. All right, so let's see what happens if I let u be cosine. Then my du is negative sine x dx. I have the sine x I need, I have the dx I need, I'm off by a negative. Well, if I multiply by 2 negative 1's, that balances to 1. So again, I'm multiplying by 1 in a clever form, and I'm going to use one of those negatives when I create du. The other one is going to just hang out because he didn't get used. All right, so the negative we didn't use is out front. Ignore the endpoints on your integral for a second. I used up my numerator, so I have 1 left. Cosine squared becomes u squared. Everything else got used to create du, to balance du. Okay, so when you're doing substitution with endpoints, you're supposed to convert the endpoints to go with it, right? This original 0 and pi over 4, they relate to x value. This is when x is 0, when x is pi over 4. So I need them to relate to u's value. So when x equals 0, that means u is cosine of 0, which is 1. So our lower endpoint, x equals 0, becomes u equals 1. When x equals pi over 4, u is going to be cosine of pi over 4, because u is cosine of x and x is pi over 4, which is 1 over root 2. So our upper limit of integration was x equals pi over 4. That's going to become u equals 1 over root 2. Now we can solve this integral. So rewrite your u squared from the denominator as a u to the negative 2, so that way we can use our reverse power rule. So I'll have a negative times u to the negative 1 divided by negative 1, evaluated from 1 to 1 over root 2. I'm going to rewrite that as just a 1 over u, evaluated from 1 to 1 over root 2. So when you put those endpoints in using the fundamental theorem, you will get root 2 minus 1, okay? You can work through the calculation there, but it comes out to root 2 minus 1. All right, so that's example 2. Let's go to example 3. Okay, so this is an interesting example. This one, there are actually 2 different u's that work. Most people, what jumps out at them is to let u be tangent, because then my du is going to be a secant squared. Because of chain rule, it's 2 secant squared 2x dx. So I have all the pieces I need, except I'm short that constant multiple of 2. So I'm going to get a 1/2 integral u du, right? The secant squared and the 2 from the numerator got used to create the du, to balance the du. All right, reverse power rule gives me 1/2 u squared over 2 plus c. Simplify and plug back in our original u, we get 1/4 tangent squared 2x plus c. So this is the way most people will go about this with u and du, but technically there's another u that works. I want to show you that. If I let u be secant 2x, then du is 2 secant 2x tangent 2x dx. So I look back at the original problem, I actually do have, if I use one of the secants for u, I can use the other secant to create du. So when we rewrite our integral for this one, I'm still going to get that 1/2 because I was missing that constant multiple of 2. And I'm still going to get u du, but my u used a secant, and my du used one of the secants and the tangent. So we still get 1/4 u squared plus c, but now my u was secant. So I'm getting 1/4 secant squared 2x plus c. Both of these are correct answers. They actually represent the exact same family of functions. If you want to see why, let's see. It's just your properties of trig. So I know that tangent squared of an argument plus 1 is secant squared of that same argument. So if I were to add 1/4 to this original tangent squared, then it would match the secant squared. And this constant c is varying through all possible constants being added. So when c equals 1/4 in the first one, it matches c equals 0 in the second. When c equals, let's say, 1 in the first one, it matches c equals 5/4 in the second. So these are the exact same family of functions. They are both correct. All right, let's look at the last one. This is another one with endpoints, so we will have to convert our endpoints when we do our substitution. All right, so this one, nothing may jump out as a good choice for you, so you start playing with things. So oftentimes a good idea to try is just say the whole denominator. It'd be nice if he was one thing. So I'm going to make the whole denominator u. Now my du then, well, the derivative of 1 is 0, derivative of x is 1, so I just get dx, du equals dx. So let's start rewriting this integral. I'll fix the endpoints in a second. So the 1 plus x becomes u in the denominator. The dx is exactly the same as du, so dx can change to du. I still have to deal with that numerator, though. The way we're going to deal with that is use our original value of u. If u equals 1 plus x, then u minus 1 is the same thing as x, right? Those equations are equivalent. So that numerator is equivalent to u minus 1. Same thing, x, u minus 1, they mean the same thing. All right. We are going to evaluate from, we had 1 to 3, but we need to adjust to our u. So when x equals 1, u equals 1 plus 1, which is 2. When x equals 3, u equals 1 plus 3, which is 4, because I just plugged in x's value into u's equation. So our new integral is from 2 to 4. All right, here we go. The integral from 2 to 4 of u minus 1 over u. Well, let's rewrite that fraction by distributing the denominator. That's why it's nice to have a single thing in the denominator I can distribute. So I get 1 minus 1 over u, and I can integrate each piece. Oops. Okay, 1's integral is u. 1 over u's integral is natural log of u. Evaluated from 2 to 4. 4 minus ln of 4 minus 2 minus ln of 2. And you can simplify this a little. If I use log properties, I can make this 2 plus ln of 1/2. But doesn't matter. So that's our answer.